The mean value theorem is a pretty simple idea. It applies to functions that are differentiable on closed intervals. A simple illustration of this, it says, well here, it says that if you have a function that is differentiable on a closed interval, ab, so I'll draw one such function. I could do, say, this. If the function is differentiable on that interval, then there must be some point in between a and b where the instantaneous rate of change is equal to the average rate of change. Now, the average rate of change is just the slope of the secant line that joins the points corresponding with the endpoints. So I have some function here, f, and its average rate of change is the slope of this line. Let me just quantify that. That is written as the change in height, so that's f of b minus f of a divided by b minus a. It's the total change that the function goes through divided by the time it takes, quote unquote, for it to undergo that change. So it says that, so it's the mean value theorem, so the mean meaning the average. So the slope is the average rate of change. The mean value theorem says that there's guaranteed to be one spot in between where the instantaneous rate is equal to the average rate, and that happens to be for this particular function right about there. In other words, there's going to be a spot where the slope of the tangent line is equal to the slope of the secant line. These lines have the same slope. And that's expressed by saying that the average rate of change is equal to f prime of some number between a and b, where c is between a and b. So that's what it guarantees. Provided that the function is differentiable and the interval is closed, there's always going to be some value of c between a and b such that this equation will be true. This is going to have some solution out there. It doesn't tell you how to find it, and in practice it doesn't really matter. It's just the fact that it's always going to be there somehow. No matter how you try to draw it, you really can't beat it. If I use a different color here, even if I go crazy, right, like so, these two functions, the original thing I drew and this green thing, they both have the same average rate of change over the interval a and b. But still, there's going to be some spot, at least one. In this case, we have two of them. I'll draw a different color. We got one right here. Slope is going to be the same, so I'll call that C1, say. And it happens to happen again here, C2. Nothing, we don't really call it anything special if it happens to happen more than once. I just like to show it, C2. So, in both cases, right, it doesn't matter. So all that it's saying is that such an equation is going to have at least one solution, no matter how it's drawn. One of the conditions for this, or for the theorem to hold, is that the function has to be differentiable. It could have a corner or a vertical tangent, or it could be discontinuous, and then all bets are off. Let me just give you a quick example of that. If the function is, say, let's say it starts here, we'll say that's A, and this will be B here. And suppose the function does, we'll do this. Let's say it goes straight there, and there's a corner, and then it goes straight up, like that. Alright, this function does not satisfy the hypothesis of the mean value theorem because it's not differentiable. The average rate of change is like so, and yet there's no spot in between where the tangent line has a slope equal to that, right? Because it's just two straight line segments. So that it invalidates the hypothesis, and therefore the theorem does not hold for this particular case. But that doesn't mean that if the function fails to be differentiable everywhere, that it's not going to happen. All right, we could have a spot here and a spot here, same kind of deal. The function comes down, has a corner, but then is nice and differentiable from there on. Right? In this case, the function fails to be differentiable at this point here, but still, you can coincidentally just so happen to find a spot where the tangent line, the slope of the tangent line, equals the slope of the secant line. Really just a coincidence, and I just show you this just to show some variation on how this thing can play out. The important thing is that if the function itself has a derivative everywhere, then it's guaranteed that there's going to be some c value inside there someplace. Let me give you a more concrete example of that. Typically this is how they go. You'll be given a function, and you'll be given an interval, and you'll say find the value of c that satisfies the hypothesis of the mean value theorem. So I'll give you y equals, if we start out with, say x squared minus 6x plus 8. Show that this function on the interval minus 1, 5 shows that this function satisfies the hypothesis and the conclusion of the mean value theorem on this interval. If you're doing problems like this, they all go exactly the same way. First thing you do, find the average rate of change. Find the slope of the secant line. Find the slope of the line that joins the endpoint. So that's step 1. Step 2, take the derivative, and step 3, set those two things equal to each other and solve for x. So the average rate of change, I'm going to ignore the graph for now. I'll come back to that. The average rate of change is just y of 5 minus y of minus 1 divided by 5 minus minus 1. When I work that out, y of 5 happens to be, we get 25 minus 30 plus 8 is 3 minus, put in minus 1, and that works out to be 15 divided by 6 is, that's negative 12 over 6 is negative 2. So that means that this function, the average rate of change on this interval is minus 2. By the mean value theorem, that means that the derivative of this function must equal minus 2 someplace between minus 1 and 5. So y prime is 2x minus 6. When I set that equal to the negative 2, I'm guaranteed to find, this equation is guaranteed to have an answer someplace, to have a solution someplace between minus 1 and 5. And it does. It's 4. 2 times 4 is 8. No, wait, it's no, it's 2, right? 2 times 2 is 4, minus 6 is minus 2, so x equals 2. And just to show, so this is where it happens. At this time, this function is changing at exactly the rate of negative 2 y units per x unit. So that's where the instantaneous rate of change equals the average rate of change. And to show that, the function itself is a parabola. It happens to look something like this. The points are minus 1 is back here, and the 5 is out here. And the negative 2 that we found is the slope of the line that joins the endpoints. Alright, there's the secant line, and we found that it's going to be parallel exactly when x equals 2. Down here somewhere, I think. Mathematically, I might have had it drawn up a little bit funny, but it looks something just like that. Alright, it's going to be right about there. So my graph is ballpark right, but that's what it's going to be, and that's how these typical mean value theorem problems go. I have another one that a professor told me about in college, which I thought was pretty interesting. He said that way back when, if you were on the New Jersey Turnpike, you have to give over a ticket between getting off on the exits. When you get on, they give you a ticket, and when you get off, you have to hand over the ticket so they know how much to charge you. And he said that they used to punch your ticket with a timestamp to tell how long it took for you to go between one exit and the other. And if your time was too small, then it guaranteed that at some point you broke the speed limit and you got an actual ticket. Let me show you an example of that. What he means is, let's say that you have two exits and they're 20 miles apart. So here's 20 miles. And you go from the one exit, you start here, And let us suppose that 17 minutes later, 17 minutes, which incidentally is 0.283 hours. Let us suppose that in the 17 minutes, you're clocked at going that 20 miles. Well, they divide that out. Now, we don't know how you got there. All that really matters is the endpoints. If you cover 20 miles in 17 minutes, that's an average speed, 20 miles, 0.283 hours. That means that your average speed is 70.58-ish miles per hour. That guarantees that at some point on your journey, remember, this is just the average speed. This doesn't tell you where you actually were. On average, you went 70.58 miles per hour, which means that you guaranteed you broke the speed limit at some place, at some point in time between when you started and when you arrived. For example, suppose that your path suppose that you started off slow and then you speeded up and eventually got there. Well, you broke the speed limit, or rather, you were doing 70.58 miles an hour at this time here. It doesn't matter where it happened, but it doesn't really matter, because if you broke it anywhere, you broke it. No matter what path that you take, even if more than likely, when you're driving, you're probably going about the average speed for most of the time, and then you slow down. But even still, guaranteed to have broken the speed limit at least one time on your journey. Why? The mean value theorem. No getting around it. I don't know why they stopped doing that if the story is in fact true, because like I said, there's no way around it. But that's what it is. I think that's a better application than the typical textbook examples where you're just given a function and you just have to verify it. The true use of the mean value theorem, though, is which I have stated here, is alright. If it gives you a relationship between what we typically consider to be the original function and its derivative. Now we can play around here. It guarantees that if this function is differentiable on the interval AB, then this equation has to have some solution. We can twist this around a little bit. If I bring this to the other side, we get a slightly different version of this. All right, pull the B minus A over. And another way to look at it is the difference in the original function can be represented by the value of by the length of the interval, right? The length of B minus A multiplied by the value of the derivative of that function at some specific point, right? So there's a way to trade up differences in a function for a single value of its derivative multiplied by the interval over which it is taken. And yet, so this again is just a restatement of a relationship between a function and its derivative. But yet another way of looking at this is if you consider this to be the original function and these to be antiderivatives of this, rather than focusing on this and going this way, which is typically done, we can start out over here and say, we can talk about this function versus its antiderivatives. It says that if I switch the notation up just a little bit, the value of a function at some point multiplied by a distance can be equal to the difference in that function's antiderivatives. Right? I use a capital F to represent an antiderivative. So we start out here, this can be represented that way. The way that we use this, I'm going to hopefully I can get into detail with this in a different video. But all that means is, if this is the little function, little f, the amount by which its little f's antiderivatives change can be written as the value of that function at some point, someplace, multiplied by the length of the interval. Let me just restate that again in case that was unclear. The other way to look at the mean value theorem is that the difference in the antiderivative of some function can be traded in for the value of that function somewhere multiplied by the length of an interval. So that means that the difference, so here's f, here's little f, the difference in f's antiderivatives on AB can be represented by this length multiplied by f of some number in here someplace. And it just so happens to look, I'm thinking maybe it's about there in this particular case. See, you find out at some point during your calculus class that the area beneath a curve, beneath an f of x curve, right, the area stands for the change in a function's antiderivatives on that interval. And we can rewrite that change. So this area is equal to, if you were to take this area and smush it into a rectangle, there's guaranteed to be some point where you can exchange expressions that look like this for expressions that look like this, and it's all about the areas, where the area of the box here, there's guaranteed to be some height on that interval where if you pick it, it'll just equal the actual area under the curve from A to B, so that we have an equivalence here. Let me just circle. I want to point these out. So we got this here. Okay, the height of this rectangle is f of c, some number in there. I drew it where it looks like it's going to work, but that is equal to, so that's the left-hand side of this. That's this, all right? The b minus a and the f of c. I happen to pick a c that looked nice, right? Versus this area here, which is the right-hand side. Right, guaranteed to be a spot where the area of the rectangle equals the area under the curve.